Optical communication. Optical wireless technologies for 5G/6G and IoT. By Ali Othman. Agenda style. 1. Abstract. Introduction. 2. OWC benefits over existing technology. Possible characteristics. Why should we use OWC? 3. Integrating the Internet of Things in 5G/6G. Challenges to the OWC. 4. Application. Conclusion. Abstract. Optical wireless technologies have recently received a lot of interest due to their effectiveness in communication. It may be used to bring 5G and 6G into the real world in a variety of ways. This paper presents a survey of the literature on wireless optical technology. From optical wireless and 5G/6G and IoT to integration approaches and difficulties, a wide range of subjects are covered. This section discusses a few of the most important technology applications. There have been conclusions formed about its role in bringing 5G and IoT to life. Introduction. Optical wireless communication has revolutionized the number of devices connected to a network in unprecedented ways. The Internet of Things, IoT, is a revolutionary new network technology that connects everything. RFID tags, mobile phones, sensors, and actuators are all included in this umbrella category. Another potential IoT capability is tactile Internet. 5G and the Internet of Things, IoT, will have a large device communication network, be energy efficient, and give high-quality experiences. Between 2027 and 2030, 6G mobile phone networks are projected to debut. Radio frequency technology is used in almost all wireless communication nowadays. 5G and IoT networks have requirements that go beyond radio frequency-based wireless communication. To address increased demand, scientists are developing a new spectrum. Optical wireless technology benefits. In a number of crucial areas, this technology will exceed 4G, making it capable of supporting a wide range of services and applications with a wide range of needs. The theoretical and optimal standards have been completed, and the system will be completely operational by 2025. 1. High traffic volume. Wireless devices will be linked in higher numbers than ever before, and cellular data capacity per region will be thousands of times greater than it was with 4G networks in the beginning. 2. Massive connectivity. Thanks to 5G, massive connectivity will be available. The number of devices connected will be 10 to 100 times higher than with 4G. 3. High user data rate link. Users will be able to accomplish up to 10 Gbps, which is 10 to 100 times faster than 4G. 2. 5G networks must be able to accommodate exceptionally high user data rates. Users will be able to achieve up to 10 Gbps, which is 10 to 100 times faster than 4G. 4. Low energy consumption. The infrastructure for 5G connectivity must be energy efficient. It will result in a 90% reduction in energy use. 5. The response time is really short. The response time will be in the sub-millisecond to millisecond range from start to finish. Optical wireless technology characteristics. 6G network standards are being developed by researchers. Ultra-high device bit rates are one of the most significant needs for 6G. Furthermore, 6G is expected to provide 1,000 times the capacity of 5G. Wireless connections. The customer wants less than 1 millisecond latency. 6G is expected to provide superior wireless security, reliability, and power efficiency, as well as massively connected complex networks, in addition to spatial multiplexing. 3. To handle 5G wireless communication devices, networks will require unique characteristics. Future 5G and 6G networks will have the following notable characteristics. 1. It is desirable to increase spectral efficiency. In 5G systems, several input-output ports, complicated coding and modulation techniques, and a one-of-a-kind waveform designs are all designed to maximize frequency, spectrum utilization. Spectral efficiency in 5G networks should be 3 times as high as in 4G networks. 2. Low-priced. In terms of data transit per unit of energy, 5G is predicted to be 100 times more efficient than 4G. Low-cost network technology, low-cost deployment, and more energy-efficient network and user devices are required for all of these issues. 3. Indoor rerouting of high traffic. Indoors generate 80% of mobile traffic. By sending data to indoor microcells, macrocells are freed up. In 5G and 6G networks, data offloading to microcells becomes crucial. Optical wireless technology characteristics. The figure depicts a terrestrial optical wireless communication (OWC) system. Optical carriers are modified with information waveforms at the transmitter. Due to the signal's loss in transmission over the channel, the information received may not be an exact copy of what was originally sent out. Transmission loss is mostly produced by molecular components that are scattered or absorbed along the transmission path. Why use optical wireless? The frequency range of the radio spectrum is 3 kHz to 300 GHz. Existing wireless devices operate in the frequency range, 3 kHz to 10 GHz. This frequency is gradually declining, and it will soon be unable to handle the networks of the future. V2X, subsea, cellular, space, smart retail, e-health, and smart homes are all supported by the OWC networks. The network is governed by both domestic and multinational bodies. Integrating Internet of Things in 5G/6G. Integrating Internet of Things, IoT, applications into 5G networks is becoming a popular study topic. While M-Wave technology was once thought to offer significant advantages in terms of high spectrum availability, it is now believed to be incapable of performing this function on its own. Integration of IoT services in 5G technology will be simplified by combining all 3 technologies: massive MIMO, millimeter wave, and dense tiny networks. Challenges. 1. Frequent handover. Micro networks with frequent handoffs will be the future of communication. Handover between optical and radio networks. Small optical cells induce unwanted handovers. In tiny networks, prevent ping-pong and needless handovers. 2. Intercell interference. VLC and Li-Fi networks need to control optical interference between cells. OWC LEDs are widely used and may cause 5G/6G and IoT network interference. Thus, intercell optical interference is difficult to resolve. 3. Loss due to atmospheric changes. Air absorption, free space loss, and atmospheric scintillation all have an impact on the performance of an OWC. It's difficult to reduce air loss in 5 GB networks and considerably more difficult outside. 4. Limited uplink communication using OWC technologies. Low-power LEDs make VLC and Li-Fi uplink transmission challenging. Because most user equipment is uplink, transmission capacity is limited. High-power downlink lighting can readily affect LED dispersed light. 5. Flickering avoidance. Various OWC modulation schemes might generate dangerous flickering. Flickering is a perceived fluctuation in light brightness. This harms human health and can be avoided by carefully adjusting LEDs. 6. An increase in FSO's backhaul data rate. Networks must be able to handle massive amounts of data traffic in order to provide users with high data rate services, such as voice-on-data connectivity. Application. OWC can enable high data rate 5G communication and ubiquitous Internet of Things connectivity. OWC technology can securely connect a wide range of 5G devices for both indoor and outdoor applications. OWC is used for IC interconnects, inter-building connectivity, and satellite communications. 1. In health application. The performance of many medical devices can be adversely affected by electromagnetic interference, EMI, from radio frequency, RF, EMR. This study focuses on RF-based wireless healthcare technologies. Future studies should investigate LED-based OWC. 2. In vehicular communication. WAVE employs an unlicensed RF frequency for IEEE 802.11p. Traffic management can benefit from the OWC system. Thus, OWC-based vehicular communication research may be fruitful. Wireless access in vehicle environments, WAVE. 3. For positioning. LED-based indoor positioning systems have gained popularity due to their accuracy, license-free operation, EMF interference, and low-cost front ends are some aspects to consider. The use of optical wireless technology for outdoor positioning may be a future research area. 4. In drone application. Drones are being considered as the next step in transportation. Large-scale deployment of drones raises a number of challenges, including exact localization and reliable communication among the drones themselves. Conclusion. In the future, no other technology will be able to satisfy the needs of 5G/6G and IoT networks. Wireless radio frequency and optical technology make this possible. OWC technology can provide a high data rate of roughly 30 gigabytes per second. Another significant necessity for expanding the reach and capacity of a mobile network is the reuse of existing resources. 5 gigabyte systems need a lot of capacity, a lot of connectivity, a lot of latency, a lot of security, a lot of energy, a lot of user experience, and a lot of dependable connections. Thank you.